Swayam Prabha. Digital India. Educated India.
In the previous lecture, we discussed collision, and in this lecture that follows that one, I am going to solve two problems on collision in 2 dimensions, and it will give you a feeling for the collisional problems and how the momentum is transferred from one colliding particle to the other colliding particle. So, in the first problem, we say that a ball of mass m collides with another identical ball at rest, and the collision is elastic. What that means is that the kinetic energy is not lost. Show if the collision is not head on, that means the point at which the collision takes place is not along the line of motion, and I will explain this in the picture in a minute. Then the two balls move at 90 degrees to each other. After the collision. So, what is happening in this problem is, here is a ball at rest, and this is in the plane of this screen, and another ball comes in with the center moving like this and collides with this ball. Now, when it collides, make it here, this is not head on. That means the line along which it was moving, the point of contact where the collision takes place, is not on that line. You can see from the collisional point of view that as it collides, the forces are going to be perpendicular. The impact that the two balls have, the forces generated or the impulse generated, is going to be perpendicular to their common surface at the point, and therefore, it is going to be in the direction like this, perpendicular. Since ball 2 was initially at rest, is going to move exactly in the direction of the force. Ball 1, which was coming in, experiences an impulse like this, and therefore, its momentum, which was in the direction to the right, is going to change a bit, and it is going to move like this. So, finally, the picture that emerges is that one ball is moving like this and the other ball is moving like this, and this angle we want to show is 90 degrees. This problem can be solved using the principle of conservation of momentum and principle of conservation of energy. So, what we are given is that this ball which was coming in, at some initial velocity, let us say u, collides with another ball which was offline, and after that, let us say this ball, the second ball, let me call this 2, call this 1, it starts moving at this angle, which we already decided is going to be along the line of impulse, and let us call this angle theta 2. And ball 1 starts moving at some other angle this way, which I will call theta 1. So, this is ball 1 moving this way. and we wish to show that theta 1 plus theta 2 is equal to pi by 2. What are the equations that we have at our disposal? That's momentum conservation. And for good bookkeeping, I am called the initial direction in which the ball was moving x direction and the perpendicular direction to be y direction. Since there is no external force, momentum is conserved, and therefore Px total is same as it was earlier. Earlier the momentum was mu, and after the collision, the first ball is moving with velocity, let us say v1, and this is moving with v2, m v1 cosine of theta 1 plus the momentum of the second ball in the x direction is going to be m v2 cosine of theta 2, and you can see that m cancels, and therefore I have u equals v1 cosine of theta 1 plus v2 cosine of theta 2. I have got one equation from momentum conservation. I have got another equation from momentum conservation, that is Py total should also remain the same. And what was Py total to start with? There was no momentum component in the y direction, and therefore I am going to have 0 equals m v1 sin theta 1 minus m v2 sin theta 2. I put a minus sign here, already anticipating that the y components are in the opposite direction. If you put plus, finally you will get v1 equal to minus some v2, so that does not really matter. And this equation gives me v1 sin theta 1 minus v2 sin theta 2 equals 0. That is equation number 2. The third equation comes from energy conservation, and that says that initial energy m u square should remain the same even after the collision, because it is an elastic collision, plus 1/2 m v2 square, and again half cancels, m cancels, and I have u square equals v1 square plus v2 square. That is my third equation. Let me write them again. So, three equations I have is u equals v1 cosine of theta 1 plus v2 cosine of theta 2. I have 0 equals v1 sin theta 1 minus v2 sin theta 2, and u square equals v1 square plus v2 square. Equation 1, equation 2, equation 3. How many unknowns are there? I have unknowns. U is supposed to be known. I have v1, v2, theta 1 and theta 2. 4 unknowns. So, I cannot get all 4 quantities by solving these 3 equations. I will need some other information, but I can find relationships, and that is what we are trying to find here. We are trying to find, and we are going to show that theta 1 plus theta 2, they are going to be such that they always add up to pi by 2. So, we find a relationship. Beyond that, I cannot really find all those 4 quantities or 4 unknowns individually. So, let us now solve these equations. I square u equals v1 cosine theta 1 plus v2 cosine of theta 2. I square the left hand side, I square the right hand side, and I get u square equals v1 square cosine square theta 1 plus v2 square cosine square theta 2 plus 2 v1 v2 cosine of theta 1 cosine of theta 2. But u square from equation 3 I already know is v1 square plus v2 square, because it is an elastic collision. This comes out to be v1 square cosine square theta 1 plus v2 square cosine square theta 2 plus 2 V1 V2, this is V2 cosine theta 1 cosine theta 2. I will take V1 square and V2 square to the right hand side, and therefore I will get 0 equals minus V1 square sine square theta 1 minus V2 square sine square theta 2 plus 2 V1 V2 cosine theta 1 cosine theta 2, which I can write as minus V1 square sine square theta 1 plus V2 square sine square theta 2 plus 2 V1 V2 cosine theta 1 cosine theta 2. This I can further write, because I already know from second equation that V1 sin theta minus V2 sin theta is 0. So, I will bring it, use that equation and bring it in that form. I will write this as minus V1 sin theta 1 minus V2 sin theta 2 whole square plus 2 V1 V2 cosine theta 1 cosine theta 2, and to make this term, the term here in red box, and the new equation I am writing, I have to subtract here minus 2 V1 V2 sine theta 1 sine theta 2. Everything sits well. Now, I already know that V1 sin theta 1 minus V2 sin theta 2 is 0. So, this term is going to be 0. So, I am left with 0 equals 2 V1 V2, which I will take common, cosine of theta 1 cosine of theta 2 minus sine of theta 1 sine of theta 2. So, I get 0 equals 2 V1 V2 cosine of theta 1 cosine of theta 2 minus sine of theta 1 sine of theta 2, which is nothing but 2 V1 V2 cosine of theta 1 plus theta 2, which immediately tells me that cosine of theta 1 plus theta 2 is equal to 0, or theta 1 plus theta 2 equals pi by 2. Notice that in this problem I right from the beginning used the momentum conservation equation and energy conservation equation. Just a comment on that. So far I have used the momentum conservation equations and derived this condition just to give you a little more feel for how the momentum is imparted. Let me look at it more carefully from the point of view of the impulse which is given by ball 1 to ball 2. And as I commented earlier, the impulse given to ball 2 is going to be in the direction in which it moves, which is at an angle theta 2 from the initial direction of ball 1, and ball 1 moves like this with velocity V1 at an angle theta 1, and the ball 2 is moving with angle theta 2 V2. So, if the impulse is j, the impulse of ball 1 is going to be minus j. J vector is going to be m V2, and therefore, Jx is going to be m V2 cosine of theta 2, and Jy is going to be m V2 sine of theta 2. The change in momentum of ball 1 is delta Px is going to be m V1 cosine of theta 1 minus m u. This is the x component of the momentum after the collision. Mu is the initial x component of the momentum, and this is minus Jx, and this is minus m V2 cosine of theta 2, and if I cancel m, it immediately gives me the equation I used earlier, V1 cosine of theta 1 plus V2 cosine of theta 2 is equal to u. Similarly, delta Py is equal to V1 sine of theta 1 with m here minus initial momentum was 0, and this should be minus jy, which is equal to minus m V2 sine theta 2, which gives you V1 sine theta 1 plus V2 sine theta 2 is equal to 0. This sine problem is coming because again I am taking V1 and V2 to be in the same direction, but that is not a problem. So, what you see here is that this equation of momentum conservation actually comes from Newton's third law, where J are acting in equal and opposite way on the two balls. The next problem I am going to solve is again a two-dimensional problem, and it is based on the familiar game that you all play, is carom. So, I am going to say a carom striker has diameter 4.1 centimeters and weighs 15 grams. It is moving with speed 2 meters per second along x axis. It strikes a stationary carom coin that has diameter 3.1 centimeter and weighs 5 grams. The distance of the center of the coin from the x axis is 2 centimeters. Find the velocity of the coin and striker after the collision, assuming it to be perfectly elastic, and that means there is no energy loss. So, what you are given is, here is a carom coin 3.1 centimeter in diameter, and here is a striker bigger in size, its diameter is 4.1 centimeter. It is moving along the x axis, and this fellow is at a distance 2 centimeters from the x axis. This comes in and hits the coin, and the coin will start moving. Now, notice the difference from the previous problem. Here the distances are given. So, we do have knowledge about one of the angles. So, what happens is, when this striker strikes the coin, the striker was moving like this, the distance here is 2 centimeters, there is going to be an impulse on the coin in the direction shown by green. And since the coin was stationary to start with, it is going to move exactly in that direction. So, it is going to move at an angle theta from the x axis in the direction of this impulse, and that we can easily find out, because you are given the radius here is 1/2 of 3.1, 1.55 centimeters, and the radius of the striker here is 4.1 divided by 2, and that is 2.05. So, I know this distance in the triangle, a thick green line, to be 2.5 plus 1.55, 3.6 centimeters, and the perpendicular to be 2 centimeters. So, you immediately have sine of theta is equal to 2 over 3.6, which is 20 over 36 or 5/9. So, theta at which the coin is going to move is sine inverse of 5/9, which is roughly 33.75 degrees. So, we already know that the coin is going to move at an angle 33.75 degrees from the x axis. Now, let us write the equations. Momentum conservation, which tells me that the momentum in both x and y direction is going to be conserved. Let me take this x and perpendicular direction to be y. So, initial momentum is 15 times 10 raised to minus 3. Since the units of mass are going to be grams all throughout, I do not have to write minus 3 here. So, 15 times 2 is the initial momentum in the x direction, is going to be equal to 5 grams is the mass of the coin, and suppose it moves with velocity v1, v1 cosine of theta plus 15 v2 cosine of, let us say striker now moves at an angle phi, cosine of phi. That is my equation 1. So, this is Px. For Py, initial momentum in the y direction is 0, and this is going to be 5 v1 sine of theta, again anticipating that they will move in the opposite direction in the y direction, is going to be 15 v2 sine of phi. That is my equation number 2. Equation number 3 is going to be energy conservation, and that will give me 1/2 times 15 times 2 square is 4, that is the initial kinetic energy, is going to be 1/2 times 5 v1 square plus 1/2 times 15 v2 square. How many unknowns do we have? I already know theta, so I do not know phi, I do not know v2, and I do not know v1. 3 unknowns and 3 equations. Because we already have information about theta, using conservation principles I can get these 3 unknowns. And now what remains is just solving this equation. Let me simplify them right here. So, I have 30, 15 times 2 is 30, is equal to 5 v1 cosine of 33.75 degrees plus 15 v2 cosine of phi. That is my equation 1. I have 0 equals 5 v1 sine of 33.75 degrees, sine we have already calculated is 5/9 minus 15 v2 sine of phi. That is my equation number 2, and I have half cancels, this half cancels out here. So, I can write 60 equals 5 V1 square plus 15 V2 square. That is my equation number 3. I solve these, which I will leave for you, and get answers that V1 comes out to be 2.5 meters per second, V2 comes out to be 1.39 meters per second, and phi comes out to be 19.5 degrees. I will leave the solution, getting the solution for you for these equations. So, you saw again that with the information available, I could first find out in which direction coin is going to move, because it was stationary. So, it moved in the direction along the normal of the two common surfaces at the point where the coin and the striker were meeting. And once I found that direction, I had one angle already, and now what we were left with were 3 unknowns, and those we could solve with the help of conservation equations.